As we continue on with our series about EKGs or electrocardiograms, I'd now like to devote some time to thinking about exactly how charges behave inside the heart. So far, we've discussed charges in a general context, but now is the time to move on and apply what we've learned from our previous discussions on these general situations to detecting charges inside the heart rather than anywhere else. So to get ourselves started, let's think back to all of our previous scenarios where we had a box, just a square, with some charges inside of it. Now we already know what each of the positive electrodes is going to detect in each situation. It's going to detect a positive voltage for the top box, and it's going to detect a negative voltage for the bottom box. But what if we erased the boxes, left the charges as they were out in the open air? If we did such a thing, then we would see that even though the boxes are gone, the electrodes are still going to detect exactly the same thing. The voltages won't change. Now, this might seem silly to be talking about, but the point of me telling you this is that the concept of using boxes all the time was just to simplify our understanding of how charges are detected by electrodes. In fact, you could pretend that each box is a cell inside of the heart. So, cells are typically relatively negative on the inside compared to the solution that they sit in. So the inside of the cell is negative, but it's balanced on the outside with positive charges. This would mean that if you placed your positive electrode right inside of the cell, you would expect to get a voltage reading that's negative, like so. But say instead of that you decided to put your electrode somewhere far away, like out here instead. So the voltage you'd expect would actually be neutral or zero, and the reason is because typically when an electrode is far enough away from a cell, which is what tends to happen when we're measuring it in a normal person, the positive and the negative charges are considered to be close enough together so that there's really no difference in the distance between the positive charges on the electrode and the negative charges on the electrode. So we just set up a schematic of a cell. Now let's start thinking biologically about the system that we've just set up. So say we have our cell again, and remember that it has a negative charge on the inside. And so what voltage you expect to get out of a reading from the cell, if we put our positive electrode inside of it, would be, as usual, our negative voltage, like so. But the cell in the body doesn't sit by itself. A bunch of cells tend to sit together. And so I'm going to represent that by making a gridded box where there are a bunch of these so-called cells put together. What would we expect if we put our electrode in this group of cells? Well, all the cells each have a negative charge, and so there are more negative charges in this group of cells than there were in the single cell. And more negative charges means that the electrode is going to detect a higher voltage. Now, the reason I'm talking about groups of cells all at once is because in the end we're going to be talking about the heart. And the heart really is nothing more than a group of many, many, many cells. And throughout this presentation, I'm going to be representing the heart as this group of cells. Okay, so we have our group of cells, and each one of these cells in the group has its own personal negative charge, and we're using this group of cells, or this diagram, to represent what a heart would look like in a person's body, just schematically. If we were to do an EKG reading on this hypothetical heart, what would we expect to see on our voltage tracing? Well, first we have to think about other complications in the system. So the first is that these negative charges aren't unbalanced. There are actually a bunch of positive charges that balance them out that are sitting in the solution surrounding the cells. Also, we have to remember that our electrode is not sitting directly in the heart like this. Instead, our positive electrode is sitting far, far away. And the reason is because when we have a patient sitting in the office, if we wanted to measure the activity of their heart, we don't cut the person open and stick the electrode right inside of their heart. We place it on the person's skin. And the skin is actually pretty far away from the heart, so far away that if we were to detect any voltage, it would be 0, like this. So our result would be a really boring voltage tracing. It's just a flat line at 0. So if our voltage tracing from an electrode placed on a person's skin is going to be so boring for monitoring the heart, then why do we bother to do it at all? Well, actually, a cell doesn't just sit there being negative all the time. It actually has some electrical activity, which means that the charges in the cell change in their positivity versus their negativity. To help you understand how this happens, I'm going to walk you through some examples, and I'm going to be showing you the various components of a cell. So here I have a schematic of what a cell would look like that's a little bit more detailed than what I've been showing you before. So the first thing that I have drawn in the very center of the cell is sort of an outline of a blob, and I've used this to represent a structure in the cell known as the endoplasmic reticulum, or ER for short. And the endoplasmic reticulum is important to this discussion because it's kind of like a sac that sits on the very inside of the cell, and it holds certain things that are valuable to the cell, but it doesn't let the rest of the cell have it until there's a key moment. And one of the things that it holds inside of it is calcium ions. So let's say we have this cell, all of its component parts are labeled, and the cell starts out at rest, meaning that the inside of the cell is more negative than the surrounding solution. Well, this resting cell is in for a wild ride because a resting cell inside the heart actually undergoes an important cycle where all of the ion channels alter the balance of negative versus positive charge inside the cell. The first step in the cycle occurs when there's a disturbance in the solution surrounding the cell, and the disturbance is usually an increase in voltage. This voltage increase excites the sodium channel in pink, and when the sodium channel gets excited, it opens and it allows sodium that sits on the outside of the cell to come pouring inside the cell. And as more sodium ions enter the cell, the inside of the cell starts becoming positive with respect to the solution surrounding it. This causes the cell to become in an excited state, also known as a depolarized state. So the next thing that happens follows because of this increase of positive charge inside the cell. The positive inside of the cell causes the calcium channel to get excited, and it opens, and as a result, all of the calcium that is sitting inside of the endoplasmic reticulum leaves, and it enters the inside of the cell. And this causes an even more accumulation of positive charge inside of the cell. But it also causes something else, and that something else is that calcium ions have a special activity, and that activity is to be able to activate other machinery inside of the cell that causes the cell to contract or to get smaller. This is very important to the heart's function, because if a heart needs to contract, that means each and every one of its cells needs to contract, and calcium ions are the thing that cause the contraction to happen. A cell in this state is said to be excited again, but it's also contracting. So a cell can't stay excited and contracting forever and ever, because after all, the cell has to undergo a cycle. It has to go back to the way it was before in order for the contraction to happen again. And the way this happens is there has to be some kind of machinery to reset the cell to its natural or its resting state. And one of the things that allows the cell to reset is the potassium channel in blue. And what the potassium channel does is it lets potassium ions, which are sitting inside of the cell, escape and go out into the neighboring solution. As a result, positive charges are leaving the cell, and that means that the inside of the cell starts becoming negative again. Such a cell is said to be repolarizing, which is one of the first stages of resetting. So looking at this cell, we could go ahead and say, oh, well, things are back to how they were before. The inside of the cell is more negative compared to the outside of the cell because of our good old potassium channel. But if we were to just leave it at that, we would be mistaken. If you noticed, we asked sodium ions to come inside of the cell in this part of our diagram. Then we asked potassium ions to leave our cell in this part of our diagram. And the only way to get the cell completely back to normal is to put the sodium and potassium back where they belong. Well, that's where the last component of our diagram of the cell comes into play, our red sodium-potassium pump. So what it does is it brings the potassium back inside and it pushes the sodium back outside. And thus, the cell remains negative on the inside, but the proper balance of sodium and potassium are restored. The cell that is undergoing this process, we'll just label it as a resetting cell. But in reality, there's really no formal name for this stage in the cell's cycle. And once the resetting process is complete, the cell goes back to being at rest and it's ready to undergo another cycle of excitation. So the reason I walked you guys through this cycle of how a cell goes from rest to getting excited to going back to rest again is to illustrate to you that our previous concept of what cells were, which was our box with a negative charge on the inside, was kind of simplistic. And the reason was because we were always considering the charges on the inside of the cell to remain negative, when in reality, the cell is actually going from a state of being negative to becoming positive to becoming negative again. In other words, it's more like a blinking flashlight turning on and off and on and off again, rather than just something that's sitting statically inside the heart. This means that if we electrically monitor the heart with electrodes sitting on the patient's skin, the voltage tracing that we would get is not going to be as boring as we thought, because the cells are blinking on and off, turning from negative to positive. So what would we expect if we put our electrode directly inside of this active cell? So our cell starts out at a negative voltage because at rest the cell is negative, and then it gets excited and becomes positive really quickly, and then it stays positive because of the calcium ions that come out of the endoplasmic reticulum, but eventually as the cell resets, the voltage falls off again, coming back to its baseline, which is negative. The diagram I've just drawn for you, while it's rather distorted, is a simple illustration of our cardiac action potential. And all that means is that it's a diagram of how the voltage changes on the inside of the cell compared to the outside of the cell over time. Okay, so now we understand what the electrical activity of a cell would be, but we want to monitor the electrical activity of the heart. And the heart is composed of many cells, not just one. So how did the cells all acting together look, and how does that affect the electrical activity of the heart in sum? Well, the first thing to understand about cells in the heart is that they're actually physically connected to each other by structures called gap junctions. And gap junctions are basically channels that sit between cells that allow charges to move back and forth between the cells. This means that if one cell gets positive, then eventually all of the cells will become excited and depolarized and positive on the inside as well. What tends to happen inside the heart is that one cell will become positive, and the surrounding cells will pick up on that change in charge, and they will also become positive on the inside due to the gap junctions. And the positive charge continues to spread from cell to cell in the heart as the positive charge of one cell causes the next cell over from it to become excited. But eventually the heart cells all have to reset and go back to their negative state. And this too also occurs in its own wave. So you start out with one of the cells becoming back to normal, and eventually this spreads, and eventually the entire heart goes back to being in the totally negative state. Now keep in mind that this occurs over and over again. So if we look at our box of cells again, the effect of this is that we see a wave of positive charges that are moving through the heart. And then after that, we would see a wave of negative charges coming in to replace the positive charges. Now notice here that I've used arrows to depict each of these waves. And as from our previous discussions, we can call both of these arrows as vectors. And the reason I'm saying this is that the arrows not only show the distance that a positive or a negative charge has to travel, if, say, it has to go from one side of the heart to the other, but it also shows the direction of that path, and that makes it a vector. So now let's say we wanted to detect this activity inside the heart, and we wanted to do that by placing electrodes on either side of the heart. So what would our voltage tracing look like if we were to place our electrodes in this position? Let's draw a vector, yet another one, between the negative and the positive electrodes. And if you notice, the blue, the black, and the red vectors are all running parallel to each other. So that means that charges, which are moving through the heart, are actually moving on the line between the electrodes. So if we were to look at our wave of positive charge moving throughout the heart, what would we expect the voltage tracing to look like in that situation? Well, remember that the heart starts out completely negative, and if we were to go back to our previous diagram of the heart, it's in this state. It starts out completely negative, and our electrodes are actually going to see exactly the same thing. The negative electrode is seeing a mass of negative charges, the positive electrode is seeing a mass of negative charges, and so because there's no difference in what the electrodes are seeing, there is going to actually be no voltage that is recorded. So you'll get a flat line and it's at 0 volts. And then as the wave of positive charges starts moving from the upper left-hand corner of the heart to the bottom right-hand corner, you're going to see a positive deflection. And the reason is, if you think back to some previous examples of how charges move, in this example where a positive charge is moving closer and closer to a positive electrode, the voltage is going to get more and more positive. And this situation in the heart is no different. There's positive charge moving closer and closer to a positive electrode, so you're going to see a positive deflection. But then something quite curious happens, and the voltage tracing does not stay in a positive state. It doesn't stay up here. Instead, what it does is it comes right back down to the previous baseline of 0 volts. So why would that happen? Well, let's think back to our diagram from before. So remember that the heart started out negative, which is shown on the very left side of the diagram, but then it ended up being completely positive. And if we were to place our electrodes on either side of this heart, we would see that again, the negative and the positive electrodes are seeing exactly the same thing. They're both seeing a hunk of positive charge. And so there would be, again, no difference or no voltage detected. And so we would again have our flat line at 0 volts. And so that's exactly what we see. The voltage tracing comes back down to 0, and this holds whether there's a wave of positive charges that's establishing complete positivity of the heart, or a wave of negative charges that's establishing complete negativity of the heart. If the heart ends up to be completely one thing, then the two electrodes on either side of the heart are going to detect exactly the same thing, and you're going to get a baseline flat line voltage. Okay, now let's say for a moment that you decided to put your electrodes somewhere else. So if you put your electrodes on either side of the heart in this position, what voltage would you expect? Well, let's draw another vector between our electrodes. And if you look really closely, you'll see that the pink vector that I've drawn in here is actually perpendicular to the black and the red vectors, or they're at right angles. So what does that put on our voltage tracing? Well, let's think back to an old example where we have a charge moving inside a box. And let's say that it's moving at right angles to the path of the electrodes. Well, remember from this example that the voltage is not going to change if the positive charge moves up and down in this diagram. So while our heart starts out at baseline, it will continue to be at baseline as long as that positive charge moves along the line that is perpendicular to that vector between the electrodes. And the reason it's detecting a flatline voltage is not because there's no electrical activity in the heart at all, it's just because the electrodes are positioned so that they can't really pick up anything. Okay, So we have covered a lot in this video, and now what I'd like to do is to summarize the concepts that we have talked about. The first thing that we talked about is our concept of what the heart is. And we can actually think of the heart simplistically as just a box that contains many charges. Thinking about the heart in this way makes studying EKGs a bit easier. The second concept we covered was how each heart cell behaves electrically. So we know that a heart cell at its resting state is more negative on the inside than on the outside, but as time moves on, the cell undergoes a cycle of electrical activity in which it turns from its negative state to a positive one and then back to a negative state, and this happens over and over again. Then we went on to talk about how the behavior of individual cells of the heart affects the behavior of the heart in sum. So we learned that because heart cells continue to blink on and off, waves of positive and negative charge move from one side of the heart to the other. And the reason they can do that is because of the presence of gap junctions, which allow charges to move between cells. So let me take this moment then to put what we have learned in the context of EKGs. The point of EKGs is to detect electrical activity of the heart. And what I mean by electrical activity is these waves of positive and negative charge that we have just addressed in our video, moving from one side of the heart to the other. And so the final concept that we covered was how well these electrodes detect the waves of positive and negative charge, aka vectors. And how well they do detect these waves depends on how the electrodes themselves are positioned with respect to the waves of charge, or in other words, the way they are positioned with respect to the charge vector.